In this video, we will execute two Mathematica codes to fit the UV-Vis spectra for evaluating the average size of metal nanoparticles, for example gold, silver, or any other type, using the Mie model for spherical nanoparticles and Mie Gans model for non-spherical nanoparticles. We will use two Mathematica codes MGFit and LNMGFit based on the Mie and Mie Gans models to fit the UV-Vis data to determine the size, shape, concentration, fraction of spherical to non-spherical nanoparticles and their size distribution. While fitting the UV-Vis data of nanoparticles, focus is made on the surface plasmon resonance fitting. It has been successfully applied to free and functionalized metal nanoparticles in various solvents or matrices with diameters in the range 4 to 25 nanometer. Despite the differences among samples, an accuracy of about 6% on the nanoparticle's average size with respect to the sizes measured by transmission electron microscopy. Moreover, the fitting model provides other information not available from TEM, like the fraction of spherical to non-spherical nanoparticles, as well as the concentration and size distribution of nanoparticles in the sample, which is particularly useful for measuring aggregation processes. Surface plasmon resonance. The phenomenon in which the free surface electrons in metal nanoparticles collectively oscillate in resonance with the incident light is called the surface plasmon resonance. That is, when an incoming electromagnetic wave frequency matches with the frequency of the oscillation of an electron cloud, SPR resonance occurs and hence maximum light is absorbed. These resonant oscillations are used to find the size, morphology, concentration, and distribution of metal nanoparticles. Mie fitting model. The Mie model is based on the Maxwell equations accounting for the discontinuity of the dielectric constant between the metal sphere and the surrounding medium. The Mie model expressions of extension cross-section sigma external for a single sphere of radius r are given by this equation. This is the extension cross-section and AL and BL are given by these relations. Here, K is the incident photon wave vector. Psi L and eta L are the spherical Riccati-Bessel functions. Nm is the real refractive index of the absorbing surrounding medium. Nr is the complex refractive index of the gold sphere of radius r. The multipolar order L is set to 3 for all calculations. Mie Gans fitting model. In several cases, Mie model alone is not adequate for fitting UV-Vis spectra at wavelength greater than 550 nanometer, where the absorption is larger than the calculated. This is due to the reason that Mie model accounts only for spherical nanoparticles, while nanoparticles in solution can have different structures. Contribution from non-spherical nanoparticles is fitted with the Gans model, where A over B is greater than 1 is the ratio of spherical to non-spherical particles and Sg is the standard deviation. The Gaussian probability was chosen because random processes are responsible for aggregations. Log normal Mie Gans fitting model. The Mie Gans model provides information about nanoparticles, but it does not provide data about the size distribution. In principle, estimation of the size distribution of a given monodispersed nanoparticle solution from its UV-Vis spectrum is possible. In this log normal Mie Gans fitting model, sigma is weighted by the probability given by the log normal distribution according to the following expression. where RC is the center of the log normal radii distribution, W is the width of the log normal radii distribution. Now, we will discuss the two Mathematica codes, their input parameters in execution. This is a zip folder which contains both the Mathematica codes mgfit and lnmgfit. Let me first extract this folder here. This is our UV-Vis data in text format which is to be fitted. The code needs this data in a reverse order as well as in date extension. We can perform both of these tasks using Origin. Copy the data and paste in Origin. Select both columns and right-click to go to reverse order. Now to save it as a date extension, click File, Export as ASCII file named as sample. Now copy the dielectric constant file to the SPR fit folder. This dielectric constant file is for the gold nanoparticles. For other types of nanoparticles, its own dielectric constant file is to be provided. In the video description, I have provided both the gold and silver nanoparticles dielectric constant files. Start the mgfit. Make sure before running this code that Mathematica must already be installed. This code has three sections. Section 1 is related to the file import, Section 2 to the Mie fitting, and Section 3 to the Mie Gans fitting. In Section 1, file import details are discussed. Let's first copy the SPR folder to the directory mentioned here. The sample.date we have already saved to the SPR fit folder. Set wavelength normalization interval in nanometer, which is usually the start and end of the SPR absorption peak, which we can observe in Origin for our data. This subsection vertically translates spectrum when 1 and leaves the same when 0. This set the desired value of absorbance at 1000 nanometer, which is almost 0 as shown here in the profile. From here, the code starts for normalization of experimental data to be fitted as per our provided details above. We don't need to change anything here unless required. Here it will find the location of SPR maximum, which is in this case 515 nanometer. We can run the individual cells for checking the fitting status by clicking Evaluate and then Evaluate Cells, or at the end of the code by clicking Evaluate Notebook. In Section 2, details of the Mie fitting are provided. Here we will set directory of metal dielectric constant file and its name is palikgold.txt. We will write the matrix or solvent refractive index. For example, in the case of water, it is 1.33 and glass is 1.54. The value of A parameter coefficient and third order polynomial approximation are like these. They are not to be changed abruptly, but as per details provided in the referred article. Here we will set the radii interval of the fitting in nanometer, start and ending values with a step size. As discussed in the presentation, the multipolar order of the Mie calculation is set to 3. The wavelength interval of the fitting in nanometer is set in a certain range which we will be repeatedly changing for obtaining the right fitting. Again, this is the wavelength normalization intervals of SPR spectrum. The yes command overlapped the calculated SPR maximum on the experimental one. Based on the nature of metal nanoparticles, their respective data is provided here. For example, for gold nanoparticles, the bulk frequency, Fermi velocity, atomic density, and effective mass of the electron. Here the code for the Mie fitting of experimental data and the initialization of the Mie Gans fitting starts, which includes some constants and equations. We don't need to change anything here. Based on our input, it will start putting the radii 1 to 10 nanometer, in this case with a step of 1 nanometer. 1 minus RSS will be reduced to 0 for good fitting. Best radii are calculated with the reported A and shift values. 3 average radii values in the form of R1, R2 and R3 are derived with the experimental and fitted plots. The plot data is exported in normalized form. This is the last section which accounts for the spherical and non-spherical nanoparticles through Mie Gans fitting. As usual, here we set wavelength interval of the fitting in nanometer. We can play with this value during the fitting procedure. This is the normalization interval of wavelength of experimental spectrum, which may not be the same we used for Mie fitting in section 2. Here we will set fitting interval for the percent of spherical nanoparticles. For example, we start with a minimum assumption that approximately 85% of particles are spherical. We keep the step size as small as 0.01. In case we get exactly 85%, then we will have to increase this percentage. However, usually such a percentage is higher than 90%. Now, fitting interval for the Gaussian distribution of aspect ratios of spheroidal nanoparticle is set here. The center of the Gaussian distribution is set to 1, while the vertical offset of the same distribution is set to 0. Here, the Gaussian distribution list range is defined from 1.1 to 9 with a step of 0.1. Based on the fitting results, we can play with these values. We can define the spheroid volume as R cube or A times B square. For simplicity, we go on with spherical volume. To save time, we skip the best fit for each Gaussian distribution considered. However, it can be changed if fitting distorts. Finally, we plot the fit for each combination of parameters R, SG, and sphere percent. This ends our input section. From now on, code for the involved equations is written here. We don't need to change anything here but to only play with our input parameters. As the code is executed, it gives in intermediate details of the fitting procedure by incorporating the radii from the defined range and giving the percentage of spherical particles. As the calculations goes on, the decrease in 1 minus RSS value indicates a good fitting. And here is the final best fitting stage. In the best fit, it calculates the radius of the nanoparticle and the percentage of spherical particles. Finally, the data files are exported to the SPR fit folder. Now, let's run the code to generate the data files for plotting in Origin. We save this data in a folder before starting the LNMG fit. For the size distribution of nanoparticles, we will execute the LNMG fit code, which works under the same parameters as for the MG fit. Section 1 is the file import like the previous, and all the inputs are the same. It will locate the position of the SPR of nanoparticles in the experimental spectrum. Section 2 is the Mie fitting and fitting initialization. The input parameters are exactly the same as in MGFit, while the equations at the end of the code are of the log normal as discussed in the presentation. As we have provided 100 steps of execution at different radii, so it will show the results of the fitting for each execution. Finally, it has found three average radii as R1, R2, and R3. As usual, the plot is displayed and the data files will be generated in the source folder. Section 3 addresses the log normal Mie Gans fitting. Some of the input parameters are the same as in the previous for Mie Gans fitting. I will explain only those terms which are different from the MG fit. This is the fitting interval for the width of log normal distribution of nanoparticle size, initial and final values with the step size. The vertical offset of the log normal distribution is set to 0. Here the volume of the spheroid nanoparticles with average radius in the log normal distribution is preferred in comparison with the average volume. We avoid plotting the best fit for each Gaussian distribution underway. Finally, the values of each combination of parameters R, SG, and sphere percent are calculated. This ends our input section. From now on, code for the involved equations is written here. We don't need to change anything here but to only play with our input parameters. As the code is executed, it gives in intermediate details of the fitting procedure by incorporating the radii from the defined range. As the calculations goes on, the decrease in 1 minus R SS value indicates a good fitting. And here is the final best fitting stage. In the best fit, it calculates the radius of the nanoparticle and the percentage of spherical particles. It also shows the plots of fitting and the size distribution of nanoparticles. Finally, the data files are exported to the SPR fit folder. Now let's run the code to generate the data files for plotting in Origin. It is to be noted that the execution takes around 19 to 20 minutes to complete. Now we will make the data ready for plotting in origin. As the data needs to be tabulated, we will do some find and replace to make it ready for plotting. Now the data is ready and we can proceed in origin for their fitting. We will plot the Mie fitting, Mie Gans fitting with the normalized data. Thanks for watching the video.